Okay, chapter 5 is all about graphing reciprocal functions, and most people don't like it, but the truth is, once you get the rules down, it is incredibly easy. So let me just see. Yeah, that's that. So let's look at here's the big hint for reciprocal functions. Reciprocal functions will occur on a graph just like this, and they usually look like this. There's usually a area like this and an area like that. That's 1 over x, right? And the vertical asymptote is x is equal to 0, and the horizontal is y is equal to 0. But you can have them have multiple vertical asymptotes. You can have like this, then you can have a vertical asymptote that's, let's say, here. And then let's say there's another one here and another one here. And you can have these weird shapes that happen like this, and then this, and then this. And notice they tend to go back and forth into the quadrants that we're talking about. And sometimes the horizontal asymptotes can be higher than the x-axis. But let me tell you the rules. It's very simple. You're always going to have something like something on top that usually can be factored, x minus 2, and something on the bottom, right, plus 3. Whatever's on the bottom is going to dictate your vertical asymptotes, and whatever's on the top is going to dictate the x-intercepts, and whatever their powers divide into will dictate the horizontal asymptote. Let me give you an example of the horizontal powers. If I have a 3 up here, 3, let's do full size, and actually let's get rid of that. Yeah, that's still not good enough, so let's make this smaller. Actually, I don't need it at all, so let's do that. Let's get rid of this entirely, and let's start a fresh one. If I have 3 up here, let's say, and I have x plus 3 and x minus 2 and x, let's just say x, and down here I have x minus 2 and x plus 2. Actually, let's do x minus 4 and x plus 2. Notice none of them cancel out, so let's forget about cancels out for one more down here. Let's do one more like this. X plus 1, or minus 1, we'll say, at the bottom. So you're going to have a denominator like that and a numerator like that. Now let's pretend all of these multiplied. You get 3 times x squared times x cubed. And the biggest power up here would be 3x cubed. And you can always tell the powers just by looking at the number in front, and even if that 3 was in the bracket over here. And you just multiply out the x's, and however many x's there are, it would be cubed because there's 3 x's. Now just be aware that sometimes you'll see a square over here, let's say on this bracket, which means this x here counts as x squared. So it would actually be 3x times x squared times x, which would be 3x to the power 4. But you can find the biggest power right away with the number that's going to be in front of it. And in this case, we don't have a square. And at the bottom, if you multiply this x times this x times this x, you get x cubed at the bottom. So that means you get 3x cubed at the top and 3x cubed or x cubed at the bottom. Do the x's are their max power the same? Yes, they are. So just pretend they cancel each other out. And that means you're going to have a horizontal asymptote at y is equal to 3. In other words, when the powers match, it's going to be whatever the number coefficient over top. Now let's pretend this is a 2 down here. And if I'd multiplied this all out, it would be 2x times x times x, and it would be 2x cubed and 3x cubed. That means the x cubes would cancel out, and my horizontal asymptote would be y is equal to 3 over 2, or 1.5. Let's keep it like that. So that means I'm claiming to have a y asymptote equals 1.5. Now, looking at the numerator, let's just pretend this denominator doesn't exist. Get rid of it. If that were the case, if that were a graph, where would my x-intercepts be? Well, on this one, it would be wherever these brackets equal to 0. So this one is when x is equal to minus 3. So that means this first bracket, minus 3 comma 0, is an x-intercept. Over here, what about x minus 2 is equal to 0? Well, it's when x is equal to 2. So the next intercept is 2 comma 0. And that's actually to the right because this last x means that there's an x-intercept at 0 comma 0. Which means I have I know the three x-intercepts. The only time this is not true is when it cancels out with the bottom, but in this case it doesn't. Or when one of these is an exception at the bottom, which it isn't. So let me just keep those copied, and I'm just going to go back. There we go. Get rid of all this stuff here. I just want to get rid of that. There we go. So far we have those as the intercepts, and I'm going to keep that 2 down here. And I'm going to say the horizontal asymptote is y is equal to 1.5. Now we're going to look at the bottom. And the bottom, the only time you can ignore these is if there happens to be a rule down here, like if one of these matched. Oh, and actually I should get rid of this +3 because it does match. So let's pretend that's not a +3 and just say that's a +2, because I don't want them to match just yet. We'll go over the matches in a second. Let's say they all don't match. At the bottom, I can see that when this will become 0 when x is equal to 4, and this will become 0 when x is -2, and this will become 0 when x is equal to 1, which means you cannot have a 0 here, because when I multiply everything out, it becomes 0 in the denominator, and you cannot have a 0 in the denominator, which means you can instantly figure out the vertical asymptotes are going to be when x is equal to 4, when x is equal to 1, which is that far right one, and when x is equal to -2. Those are the three vertical asymptotes. So now I have a lot of information. I can figure out where the intercepts are. I can figure out where the horizontal asymptote is. And sometimes, by the way, it'll cross the horizontal asymptote. We'll have to discuss that in a second. And I can figure out where my vertical asymptotes are. And here's how we're going to do it. So now we can just draw a graph like this. And I'm going to right away put my horizontal asymptote. And it helps if you label them. So I'm going to put my horizontal asymptote there, and I'm going to label y is equal to 1.5. Now I'm also going to be, and it helps if it's a little bit smaller. Yeah, that should be normal. There we go. Y is equal to 1.5. Now I'm also going to label my vertical asymptotes that I just did. So the only one that's minus is over here. X is equal to -2. X is equal to 1, and x is equal to 4. And I'm going to label them, and I can even use the same labels. And it would help if the color was the same, but it doesn't matter. It's that one, and there's this one. Great. Now, I also know that it's going to go through these points. So where are these points? And it's important to notice where they are in terms of those vertical asymptotes. Well, 0, 0 is right here. So it's safe to say that this graph probably goes through like that. But we'll discuss that in a second. Or it might do this, but I'm going to guess that it goes through for a very specific reason. So 0, 0 is one spot. 2, 0 is between this asymptote and this asymptote. So it's going to go through 2, 0 right there. It's going to be closer to this one there, like that. So I'm going to say it's safe to say that this comes up, and it's probably going to go down. Let's find out where the other asymptote is, or intercept is, and it's at -3, 0. So I'm going to do the same thing with this. I'm going to put this over here and label it, so it's somewhere here. Now this one right away, I can say, okay, I know it's probably not going to cross the asymptote so many times, the horizontal asymptote. So I'm going to quite safely say that's that graph there. And if that's that graph there and it rotates 1, 2, 3, it's safe to say that over here I'm going to have this graph here. And I'm going to verify in a second. And then finally, I'm going to take will it go through and come back? I don't know. So how do we determine that? Well, what we do is we take a value of -2 just to the right of this asymptote. Let's say -2.1. That's to the left of this 0. Actually, -1 is easy. And then we just substitute it in. Now you're supposed to make a wall to determine this, a whole bunch of series of cells. But I'm just going to plug it in. So what's between -2 and this x-intercept here? And this x-intercept is at 0, 0, by the way, so I'll also label that. It helps if you label. Right there. and this other x-intercept is at 2, 0. So I'll label that one too. So a good one to take is -1. Why? Why -1? X is equal to -1? Because it's to the left of this x-intercept and it's to this right of this vertical asymptote. So -1 here makes +2, makes -1 here, and makes a -1 here. If I multiply all this out, positive, negative, positive, this top becomes a positive. -1 down here becomes a negative, a positive, and a negative. So again, we would get a negative times a positive times a negative. We'd get a positive. So that means in between these two, I'm looking at a positive graph. So that means it's going to come down. Well, actually, the reason I know it doesn't come up and then go through there is because I don't cross the x-intercept again. Otherwise, I could say it bounces back. But it only has one x-intercept. So if I'm going to draw it, and I'll draw it in green just so it's a little clearer because I'm using too much red, it's going to come down because I know it's positive now. That's a terrible green. And it's going to go through, and then it's probably going to hug this other asymptote. How can I make sure it's going to hug this asymptote? We can take a value that's just to the left of that. Let's say 0.99. And we can plug it in over here and come up with a value. But just if I take 0.99, which is less than 1, just a little bit less than 1. So this 3, this will become positive, this will become negative, and this will become positive. So the top is going to be negative. This 0.99 will become negative, positive, and 0.99 here -1 will be negative. That's the careful one. So if I can see here this negative, and then this minus times a plus times a minus will be positive. So it's a negative over a positive, so I can already confirm that it's going to be negative. And as it hugs an asymptote, you'll find it goes way down to negative infinity or positive infinity. In this case, because it's negative, I know it does that. This last one probably also does the same thing. So let's find a value between 1 and 2. And let's just go with 1.1. So we're going to do the same thing. What's 1.1? We can get rid of those now. So 1.1 over here will be positive. 1.1 here will be negative. 1.1 here will be positive. So up top I get a negative again. And I should get rid of those because it's going to get confusing. So that means the top is going to be negative. And 1.1 over here is going to be negative. It's going to be positive. And right here it's going to be positive. So this bottom is going to become negative here. And a negative divided by negative is a positive, which means right to the right of this asymptote, it's going to be positive. So we're really going to talk about something that, again, crosses through the asymptote, comes over here, and hugs the other side. To make sure it hugs the other side, I could take any number between 2 and 4, let's say 3. Or I could also take a number that's just to the left of 4, like 3.99. 3.99, if I get rid of all these positives and negatives, and I shouldn't have written them in there so close. 3.99 will make this positive. We'll make this positive, and we'll make this positive. It will make this negative. It'll make this positive, and it'll make this positive, which means I'm going to have a negative number. So again, it's going to be down here. And then finally, I'm quite sure if I take any number to the right of 4, let's say 5, let's find out what happens. So we do 5, it's going to be positive. 5 here is going to be positive here. 5 here is going to be positive. It's going to be positive, positive, positive. So we can see that it is indeed over here. So again, if I'm going to draw this, we're talking about something like this. It's going to have the horizontal asymptote here. It's going to have those 3 verticals. It's going to be drawing like this. It's going to cross the x-axis at -3, 0. It's going to hug this asymptote, cross the horizontal asymptote, go through 0, 0, and then hug this other one down here. And then we've got another vertical here. For this other vertical, it's going to go through, it's going to cross the horizontal asymptote. It's going to go through 2, 0 again, and then it's going to hug down here. And then finally over here, it's going to hug the asymptote and hug the asymptote. Let's see. We're going to put this in here and see if we got it. All right, let's see. Yep. And we'll just get off this. And we're just going to put this right in here. Now, I could have made a mistake, but I didn't make a mistake on any of the asymptotes. So one handy thing you should always do is just put it right into Desmos to begin with. And try not to look at it right away. Try not to ruin your Oh, I got to do that. Bracket. And put this around brackets. And then divide it. And then, oh, almost. Divide it. And divided is 2. X minus 4. And actually, I'm going to turn it off. X minus 4. X plus 2. And x minus 1. And those are in the wrong order. But I'm saying that 1 over y equal 1.5 is one of the vertical asymptotes. X is equal to 4 is another. X is equal to 1 is another. X is equal to minus 2 is another. And I'm going to say the spots minus 3 comma 0 is one spot that it goes through. I'm going to say 2 comma 0 is another spot it goes through. And 0 comma 0 is another spot it goes through. And I'm claiming it's going to cross the horizontal asymptote twice. Let's see if we're close on the graph. Turning it on. Yeah, we nailed it. We nailed it. So if I go back to my drawing, there's my drawing on the left here. See? Bottom left corner, top right corner, squiggle through, squiggle through. Going back to my graph. Nailed it. Notice we can also determine, and we'll get to that in a second, we can determine where it crosses that point on if it crosses the horizontal asymptote, but we'll get to that. What's more important is you can immediately figure out the vertical asymptotes, you can immediately figure out the horizontal asymptotes, and you can immediately figure out the x-intercepts. After that, it's just figuring out what happens on either side of those. Drawing these is very easy. You should get, instead of fearing them, you should get excited about them. Now, what about the other rules for horizontal asymptote? All right, let's get to that. When I have a power up top, let's say I have 3x squared and it expands and whatever, it can be a whole bunch of things, but that's the largest power, over something that's a bigger power, like x to the 3 or x to the 4 down below. When the power up here is lower than the power down there, we're talking about a horizontal asymptote, y is equal to 0. Okay? When the power up top is larger, and remember that when the power is equal, we just take the numbers in front and we get y is equal to 3. Now, when the powers up top are higher, that's more complicated. You won't visibly see an asymptote. It's actually a diagonal asymptote, and you can figure out the formula for that diagonal asymptote, but that comes later. And you won't be able to visibly see, but it's going to do weird stuff like that on either side of that vertical or diagonal asymptote. And you won't really see it because it doesn't seem to follow that pattern. So I'll give you some examples. Always easier just to use Desmos. Okay, so here's one where we have a 3 in front, let's say, and we have x minus 1, x plus 1, and we'll say x minus 3. Okay. We're going to put a bracket around it like that. And we're going to divide it by, and we'll do totally different ones down here, x minus 5. And we're going to keep the x plus 5 for some symmetry, and we'll say x minus 2. They're all different. Now, right away, you should say, if I expand all that, up top I'm going to get x cubed, and at the bottom I'm going to get x cubed. But clearly this one up top has a 3 in front of it, so I can expect the horizontal asymptote to be y, and the bottom will have a 1 in front of it, so I can expect that to be the horizontal asymptote. Notice that sometimes it does cross the horizontal asymptote, but never cross the vertical asymptote. So right away, I have a method to figure out the horizontal asymptote. What if the top power was 1 less? So let's say it didn't have this x minus 3. Well, if I expand the top, up top, it's clearly x squared, 3x squared. And if I expand the bottom, it is clearly x cubed. It's clear that the power up above is smaller than the power down below. So that means that the horizontal asymptote will be at y is equal to 0. And again, see, it can cross and even come back. And we'll figure out a method how to figure that, crossing the asymptote. And look at that. I think does it cross over here again? No, it doesn't. Only crosses those 2 times. But there's a way to figure out if it crosses and where. We'll get to that. But it's still hugging it. Still going to be hugging it all in all spots. Now, what if the power up above is more? So we're going to bring back that x plus 3. or let's say x minus 3, and we're going to add an x plus 3. Now suddenly you can't see it, can you? Doesn't look like there's any asymptote, but in reality, there is a diagonal asymptote going right through there, and I'll show you what it is. It's going to be y is equal to, it's going to be like a 3x sort of thing, sort of like that. I'm going to get it to it in a bit, and we'll discover ways to do it. Sometimes it can cross the diagonal asymptote, but then it'll hug it, and we'll discuss it. But that's pretty close. It's not quite right. Now that's not visually visible, but I only know it's true because if I expand the top here, I get 3x to the power of 4. And if I expand the bottom here, I get x to the power of 3. And you'll learn that it ends up being a ratio of those two. So if I cancel out these, it's clear this bottom cancels out, and I'm left with 3x up top. And that's sort of where I was able to, x, 3x. And that's sort of where I was able to, there we go, come up with the diagonal. But you won't have to worry about diagonals. When the power above is bigger than the power below, just assume it's a diagonal and you don't have to figure it out. Okay, personally I like when there's a horizontal, and I like it when there's vertical. But the rules for the verticals will still take shape. We're still going to find a vertical asymptote, but x is equal to 5, x is equal to minus 5, and x is equal to 2. And so if I zoom in, and I make them all, let's make them all red. There we go. You can still see it never can cross the vertical asymptote because it can never have 0 in the denominator. And the pattern's a little bit easier to figure out. Now you can figure out, we'll get to how to graph it, but that's what this whole thing is obsessed with, and if you get good at it, it's nothing to worry about. So then they make you review your skill sets. They make you figure out if you can still factor, because you're going to have to factor some of these to figure out the x-intercepts and to figure out the restrictions in the denominator. They want you to practice factoring here to figure out the restrictions. They want you to be able to spot difference of squares even though it's in the wrong order, figure out how to factor, figure out the restrictions on the denominator, and they need you to go back and practice that. They also want you to practice your cancellation of numbers and to figure out how to solve this. This is actually a multiplication of the reciprocal of that, and et cetera, et cetera. You have to revisit all your rules for multiplying polynomials. And most of all, you have to figure out the restrictions. And restrictions happen before cancellations. Solve and check, state the graph of this, note the reciprocal, so understand the parent graph above all else. And then they want you to list the transformations to happen to these parent graphs, and that takes a little bit of time and discussion, but I want to jump straight to the questions. So you'll see they want you to discover the zeros, and they kind of break it down into two separate graphs, even though we're talking about, let's see, do they give us the full graph? Now they sort of break it down into two graphs so that you can eventually realize that this will be the numerator and this will be the denominator, and it'll still follow the same rules. And then they want you to go through all the vertical asymptotes, all the stuff. Where's the interval of increase, the interval of decrease? What happens as x reaches negative infinity, positive infinity? Where's the y value 1? So you have to set it equal to 1, all this stuff. And they just want you to practice drawing it. And we're going to get into that, but it's easier for me to just jump to what this thing is about. Now realize that when I'm doing the questions, you should stop the video and always see if you can answer it. Matching these things is super easy, and I'll show you some tricks right away. Match each function with its equation on the next page. So we need the next page. And I'm going to show you how fast it can be to spot things and how to rule out. So you always want to rule out certain equations right away. All right, there we go. All right, first of all, let's focus on the easiest graph, a line. Are there any other lines here? No, there's not. So let's see if we can find which one is a line. Woo, there it is. So right away, because there's one line, how easy is that? To just say, okay, well, there's the line formula. Where would you verify that you got the right line? Well, the y-intercept here is right there, so 0 minus 5 should be on the drawing, and there it is there. You can also plug in some points and see if they match. But right away, we've eliminated the line. put it aside. So it's f is going with that. Now, let's look at some other ones. Well, this is clearly a reciprocal, and this is clearly a reciprocal, and this is clearly a weird reciprocal, and this is clearly a parabola that's facing down. This is clearly a parabola facing up. So maybe we should focus on the parabolas facing up and down. There's a parabola facing up. It has a leading positive coefficient. We can also figure out where the vertex is. The vertex should be at 0, minus 1, because the vertex is right in there. There's no x vertex alteration, but there's a y vertex, and sure enough, 0, comma, minus 1 is. So it's over there. I added it to the wrong graph. So boom, upward facing parabola. We figured out C goes with equation D. And we just pull it aside. Let's find the other parabola. Well, there it is there. Let's confirm that's a downward facing parabola. Let's confirm the vertex. The vertex is going to be 2, comma, minus 1. Sure enough, 2, comma, minus 1 right there. So I'm going to just delete these because they're pretty obvious. All right. What's the easiest way to spot which of these belongs to this graph? Well, this one here just has a 1 asymptote. So the denominator is going to just have one thing at the bottom. And also notice that the asymptote appears to be, I forgot to get rid of all these squigglies. Notice that the asymptote appears to be roughly there. So if we can figure out where that is, that would appear to be 2.5, which means on the bottom, it's going to be x minus 2.5, or better stated, double both of them, 2x minus 5. Let's see if there's a 2x minus 5 in any of these equations. First of all, this is the only one that has a single bottom, and this is the only one that has a double, so this would have 2 vertical asymptotes, and it's quite clear. Actually, no, this might bounce back. This one will have 2 asymptotes, and we'll discuss in a second. This is the only one that has 1 asymptote, and that's the only graph that has 1 asymptote. Very easy to solve, but also if I want to look at this and solve and say where's the asymptote, I set that equal to 0. 2x is equal to 5. Divide by 2, x is equal to 5 over 2, or 2.5. So I kind of went backwards, and I already found this vertical asymptote was x is equal to 2.5. Vertical asymptotes are the easiest way to match the graph, so that's gone. Now, I can tell right away which one is which here, but I'm going to focus on this one. Can you factor the bottom one? Yes, you can. The bottom one factors to x plus 1. The denominator factors to x plus 1 and x minus 1. The numerator is still just 1 over that. So that means there's 2 vertical asymptotes in the bottom, and the vertical asymptotes are going to be when x is equal to 1. Well, in this case, the first one's x equal to minus 1. The second one's x is equal to 1 because the roots are always the opposite of the factors. And if I look carefully here, I can see that, x is equal to 1 is this vertical asymptote, and x is equal to minus 1 is this vertical asymptote right there. And I'm right away, by process of elimination, I know that last one will match that. So this B went with that graph, whatever it was. Now, you might have been puzzled and said, well, I thought this would be it. Except that when you have a square here that goes with the same root, you're going to have a bounce back. In other words, it's going to sort of come down to that and then bounce back. And notice that minus 2 would be, it would be 2 comma minus 1, which happens to be there, 2 comma minus 1. So we get this weird bounce back at there. But to understand these, the root of this one, the parent function of this is 1 over x squared. And those look like this. Because the denominator is never negative, that means the whole thing is never negative, and you would only have a thing like that. It looks like this. It's a very rare parent graph, and I wouldn't spend too much time worrying about it. But it looks like that. Let's go home to see it a bit better. There we go. It's got 1 asymptote. It happens to be where x is equal to 0. However, if you put a minus either top or bottom, the whole thing will flip, right? And then suddenly, if you put a translation to this x down here, let's say minus 2 as they did, the whole thing seems to bounce back like that. But you can create a situation where, notice that the asymptote now happens to be at x is equal to 2. But you can create a situation where if you adjust this, so what's the lowest value this could ever be? When x is 2, the whole thing comes to 0. However, if I add something to it, suddenly that asymptote disappears. And that's because this can never become a 0 now. This can never become a 0 now. Now, it could be possible that you could come up with something here that would become the equivalent. You could never also come up with something that's squared here that would come up to minus 1. to counter this so that the whole thing down here would be negative. So that means this thing here would never come out to -1. That's the only way the whole thing can become 0. So whenever you're adding something like this, you create that weird thing that just appeared. Instead of an asymptote, it suddenly becomes a bounce back. And it looks pretty weird, so you can get rid of the asymptote. But when you do -1, you still have an asymptote. That's because it's still possible to create zeros down there. And you've actually created two situations. It's when x minus 2 squared minus 1 is equal to 0. Is equal to 0. And you discover there's two spots for that. When x is 1 and when x is 3. So when you put 3 in here, 3 minus 2 squared, 1 minus 1. And when you put 1 in there, 1 minus 2 is minus 1 squared is 1. 1 minus 1 is 0. You can see that if there's a sort of translation here and a subtraction, you can keep creating these vertical asymptotes. But not so if you add anything. If you add any number, even 0.01, we'll get rid. It should bounce back somewhere. Let's see where it is. It's going to be way down. Oof. Yeah, there. It's going to end somewhere, no matter what. That's because when you add this, suddenly this 0 that could possibly be created there is nullified, and suddenly the result will never be a error in your calculator. So whenever you're adding something to something that's like this, squared, you're getting rid of that weird bounce back. Now, obviously, there, I can just do it something that's more visible. Like that, go back home. And like that. That's what happens. When I make it 0.3, it dips down lower. When I make it 0.03, it dips down even lower. But it will still stop somewhere. You just have to set this whole thing to equal. You try to figure out what the closest value to 2 is that I can get, like 2.001. So what is 2.001 minus 2 squared plus 0.03, and you get the value of negative 0.03. Let's see. Or sorry, positive. And then you got to remember that we're taking negative 1 over it. Negative 1 divided by that. It's so complicated, but essentially you're trying to get as close to 2 in the bottom as possible. And you get negative 33.33, which is my lowest point. Don't worry about that. I spent way too much time on that than I had to. All right. For each pair of functions, always read. Each pair of functions determine where the zeros of the original function occur and state the equations of the vertical asymptote. So here's the original function, which is just a line. And here is the reciprocal. So they're trying to get you to see a connection between the original functions and when they appear as a denominator. Okay? I don't really like that method. Really, they're just asking us to factor over and over again. I prefer just to factor the denominator. But they want you to see the connections between the original functions, and now when they're in the denominator, I don't really see the point, but okay. This is clearly a line, right? When does it go through the, when x is 0, what is y? So when x is 0, y is minus 6. And that's the y-intercept. It's right there, very obviously. So when x is 0, y is equal to 6. But when is the x-intercept? Well, that's when y is 0. And the x-intercept is clearly when x is equal to 6. That's when y is 0. All right. If we now put that as a denominator, what cannot go on a denominator? 0. So now if we do it like this instead, and now they just go to the, I prefer just going to this. Going to this instead, we discover, okay, well, this denominator will become 0 when this is true. When x minus 6 is equal to 0. Now we just solve it. When x is 6, the bottom is 0, which can't be. And we can just test it out to make sure we got it right. Sure enough, if I put 6 in here, minus 6, 0, 1 over 0 can't be. So right away, I discover that this is a reciprocal. But now, the vertical asymptote is where that x value is. X is equal to 6, which makes sense. Because isn't this a y, or sorry, an x translation? Because it's right beside the x. Yeah. And what does minus 6 do? It shifts the whole thing to the right by 6. What was the original function? 1 over x. Where's the asymptote of the original function? It's right here on the y-axis. Where's the horizontal? Right here on the x-axis. What was this translation? 6 to the right. So the only thing that's going to happen is the whole graph is going to be now go like this and like this. And that's where Desmos is beautiful, because you can always put it into Desmos. Sure enough, let's do that, and let's put the original. So, and go home. So there's the original, and here's the new one. Notice that the asymptote is indeed at x is equal to 6. And the horizontal didn't change. At y is equal to 0. So all that happened is it's a reciprocal function that translated 6 to the right. So it makes perfect sense that the vertical, that's another thing, that makes perfect sense that the vertical asymptote shifted to the right. What about this one? How do we solve this one? I'm going to go straight to this because I don't really care about the line's x-intercept. You just make y 0. Let's focus on this. What can't I have at the bottom? I can't have a 0 at the bottom. So when does this equal 0? Well, we'll solve it. What's the first thing I have to do? I have to subtract 4 from both sides. I get 3x is equal to minus 4. Then I have to divide by 3. So that means when x is minus 4 over 3, and if you want to prove that, you can just substitute up here for x. Okay, what happens when x is minus 4 over 3? The 3's cancel. I get minus 4 plus 4, which of course is 0. So that means x cannot be negative 1 1/3, which means for this one, I'm going to have a normal reciprocal, except the whole thing shifts to the left 1 1/3. X cannot be negative 1 1/3. Let's try this out now. 1 over 3x plus 4. There is a regular one. Just always learn your parent functions. And according to me, this will be a vertical thing at x is equal to minus 4 over 3, right? So apparently I'm saying that there's going to be a new one once we translate, so let's turn that off. Let's turn that off, and we're going to do 3x plus 4. So according to me, boom, sure enough, it's the same reciprocal, except we have an x translation, and technically it's a stretch. So how would I write that in translation form, by the way? How would I write this in correct translation form? I'll use this. Well, if I'm going to ignore the numerator and I just factor out a 3 at the bottom, I get x plus 4/3. And that tells me right away the same vertical asymptote. However, I can see that there's also a 3 beside my x. So we're talking not about a horizontal stretch, but a horizontal compression of 1/3, because the 3 does the opposite. So a horizontal compression of 1/3. And that's the correct translation of this graph here, because you always want to factor 3. Otherwise, you might accidentally think, oh, this whole thing's moving to the left by 4, because you'd think that's the translation. No. When we factor out the 3, it's very clear I've identified the correct asymptote, but that I've also identified the new compression. Very important to understand that x translations can be misrepresented, and teachers love misrepresenting it. So again, I'm just going to factor this. And what number multiplies out to minus 15 but adds up to minus 2? X minus 5, x plus 3. Verify it, make sure that's true. So that means this whole thing gets replaced here. Okay, when would I produce a 0 in the denominator? Well, when either one of those is a 0, because it would multiply the other one. So when x minus 5 is equal to 0, or clearly when x is equal to 5, or when x plus 3 is equal to 0, or clearly x is equal to minus 3. So suddenly we have our two asymptotes, so we can expect something like this. I'd take more time, but we're going to have a horizontal asymptote at the x-axis. We're going to have a vertical asymptote at x is equal to minus 3 in, let's say, green here. and another vertical asymptote, but x is equal to 5, and neither one made it into green. Maybe I can put one over it. There we go. And I would label them like this. I would always label your graphs very well for maximum points. And you can even label the horizontal asymptote if you wanted. Y is equal to 0. Why y is equal to 0? Because the one up top is a lower power than the powers down below. So it's going to have a horizontal, but be aware it can still cross. So now to graph this, I would need to figure out what happens to on the left side of this asymptote. So when x is lower than minus 3. Let's take minus 10. When this is minus 10, this is minus. When this is minus 10, this is minus. So I get 1 over, what's a minus times a minus? Positive. So positive 1 over a positive number, which means everything to the left of this will be up here. Now, it might cross the horizontal asymptote, but it's unlikely for this one because it's too simple. And then I'm going to suggest, is there an x-intercept? No, there's not. So I'm going to suggest that it probably never crosses the x-intercept. So that means it's going to stay down here. And since they flip back and forth on either side of the horizontal asymptote, I'm going to suggest that the next one's over here. But to make sure, I'm going to take a number that's way to the right of 5. Let's take positive 10. When this is positive 10, this is positive. When this is positive 10, this is positive. So it's a positive number. And I'm pretty sure it's never going to cross the asymptote because there's no way this equaling to 0 can ever happen. And I'll explain how to figure that out in a second. But let's see if we got this right. 1 over x minus 5 and 1 over x plus 3. X plus 5. Was it plus 5 or minus 5? X minus 5 and plus 3. And I'm just going to turn it off. There we go. And I'm going to make my asymptote is equal to 8, y is equal to 5, and y is equal to minus 3. So according to me, x is the vertical asymptote. And I'm also going to make my horizontal asymptote y is equal to 0, which is already there. And it's clear to me that, there we go. And if I turn them on, let's make this one a different color, though. Make them all green. And turn this on, make it, well, yeah, we can leave it blue. And now I'm going to turn on my graph. And sure enough, as predicted, it's on the above side over here. It's on the above side over here. And it never crosses the x-axis. And we'll get into that. Because the x-axis, it can only cross based on the numerator. There's no way to get a 0 up there. We'll get more into that. Don't worry about that. So, suddenly, that is... But really in this, they just want me to figure out the asymptotes, which we did. So that's the first 3. It's how to figure out the asymptotes, the vertical asymptotes. That's all they're getting at here. What about this one? You might say that can't be factored. Except that if you look carefully, this is 4x squared has a square root. It's 2x. And 25 has a square root. It's 5. So it's 2x and 5. And you put them both in brackets. And because this is a difference of 2 squares, you put a plus in the first one and a minus in the other one, which means this whole thing here looks like that. 1 over 2x minus 5, 1 over 2x plus 5. Where are the asymptotes? You make either one of those brackets equal to 0. So one of them is here, and I can tell you from the other one. So we can tell that one is at 2.5 and the other's at negative 2.5. Not that hard once you know what you're looking for. And sure enough, let's put in the original one instead, 4x squared minus 5. And according to me, the asymptote is going to be x is equal to negative 2.5 and x is equal to positive 2.5. And let's see if that's true. Did I get something wrong? I might have gotten something wrong. 4x, oh, it's 25. I did get that wrong. And let's turn this on. Why isn't that turning on? Oh, 25. 2.5. And sure enough, I got the asymptotes correct. And I kept it in the original format just to show you. This one also never crosses the x-intercept because there's no way to make that numerator equal to 0. When do things cross the x-axis? when y is 0. How could this ever equal to 0? Answer, it can't, because there's no way to make the numerator 0. Making the denominator 0 does not work. That creates a null in your calculator. So the only way you can create an x-intercept is by creating a 0 at the top. 1 can never equal 0, so therefore it never crosses the x-intercept, and it can't. All right. Next one. All right, x squared minus plus 4, you're going to find an interesting little thing. Because can x squared plus 4 ever equal to 0? Well, I told you a little while ago that when you square something over here, even if it was x, x minus 75 squared, as soon as you add something, you're never going to have a 0 in the denominator. That's because this squared will never be negative. It might be 0 when x is 75, but then when you add 4 to it, the denominator is never going to become 0. So that means whenever you have a plus 4, you can never have a 0 down here. So this thing's going to do some weird thing like that again. And because it's all positive, it's going to stay above. Now, it'd be interesting to find out where this point is or what information we can have about this. Is there a power up top? No, there isn't. So the power down below is bigger than the power up top, which means we have a y is equal to 0, and it's probably going to cross that. Or it might not. You can never have a vertical asymptote. But what happens when x squared, what's the number we get close to when x is 0? When x is equal to 0, we get 1/4. When x is equal to 0, y is equal to 1 over 4. So that means it's probably going to dip down. That's probably going to be the lowest point when x is 0. Because when x is 1, we get, oh, actually, it dips down lower. So let's see if we can figure out when x is 0, y is 1 over 4. When x is equal to 1, y is equal to 1 over 5, which is smaller. So it's going to have a little roof, the highest peak. So I'm going to predict this. It's going to hug the y-intercept, or the x-axis rather. When it comes to the y-axis, it's going to reach a maximum height of y is equal to 1/4. Then it's going to come down and hug the x-axis again. Let's give it a try. 1 over x squared plus 4. Okay, it doesn't. Let's get rid of the asymptotes from the last one. It does indeed have a horizontal asymptote. Let's see if that 1 over 1/4 is the same as 0.25, so that is indeed the maximum height. Okay. You're also going to get into ways of finding where the maximum is based on a slope of the instantaneous velocity is 0, but we're going to get into that later. All right, and the last one, when can this be 0? Well, that's a more complicated factoring, which is why they wanted you to practice your factoring. And we're going to look at that. So what am I looking for in a complicated factor? Well, it's AC, so let's identify our A, B, C, and D. A is equal to 2. B is equal to 5. C is equal to 3. And when we're factoring something that has a bigger than 1 or lower than 1 value, or lower than -1 in front, we're looking for a number that multiplies to A times C. What was my A? What was my C? So we're looking for something that will multiply out to 6 and add up to my B, which is 5. So when I look carefully, these are all plus, so that means my factors will all be positive. 6, 1 doesn't work. 2 and 3 does. So we're really talking about x plus 3. But this is a complicated one, so I have to break it up like this. And remember, there's a square here. What can I take out of the first two terms? 2x, and so I get x plus 1. What can I take out of the second terms? 3, x plus 1. Now I can factor out x plus 1 for both, and I'm left with 2x plus 3. So those are the two terms. You can verify. But here's another tricky way to do it. We figured out normally we would be happy to just do this. X plus 3 and x plus 2. Those are our two factors. However, we're not allowed to do that. We're not allowed to do that. And I'll just make a bit more space for a reason coming up. However, I can do, this is called a slip and slide method. Now I just take the 2, the number in front, A, and divide both these factors by it. So I got 3 divided by 2, And if it can make a whole number, that's when I divide it. And if it can't, I don't. Can 2 be divided by 2 here? Yeah, it becomes a 1. So clearly this factor over here can become a 1. Right? What about this? No, I can't divide that. So here's the slide method. So I can't divide 3 by 2 and come up with a whole number, so I'm going to slide it in front of the x. Did I get the same factors? Sure did. So I really love this method. It's a lot faster than grouping, and I encourage you to understand it because it's just going to save you some. Grouping is so long. Always find tricks. Sketch the graph of each function. Use your graph to help you sketch the graph. So I'm going to pause it after this because I have some things to do, but 3 is not a bad point to reach. So we're going to pull up this. We're going to just clear our sheet. And it's always good to pause these and see if you can do them first. All right, let's focus on the first one. First one's easy. I don't even know what they're doing. I just use your graph to help you sketch the reciprocal. Okay, let's do that. Well, let's phrase this the way it is. This is a line. And in the correct order, it is actually this. We're going to put minus 1x plus 5. So really we're talking about a slope that is equal to minus 1. We're talking about a y-intercept 0, 5. And now I'm going to figure out when my x-intercept is, and that's when y is 0. So when does 1 minus x plus 5 equal 0? I'm going to subtract 5 from both sides. I'm going to divide by 1. When x is equal to 5, so that means that I also have 5, 0 is my x-intercept. You can verify this by plugging in 5 for x up here. Minus 1 times 5 makes minus 5, plus 5 is 0. So here I can easily sketch it, and here's the beautiful thing about reciprocals once you have 2 points. So here's my graph, and I've already discovered it goes through 0, 5 here, and it goes through, that's 5, 0. And 0, 5 up here, and it has a basic slope of 1. So in red, this line looks like that. What were those 2 points? Well, let's mark them down. They were here, right? 5, 0, and 0, 5. What's the beautiful thing about reciprocals? They have switched numbers. And this is one of the weird cases where the reciprocal of this will be the reverse. But let's do the old algebraic way of doing the reciprocal. Let's do the algebraic way. First of all, switch to y's. Y is equal to minus x plus 5. Next, switch your y's and your x's. Okay. Now isolate your y. So you get x minus 5 is equal to negative y. Divide both sides by minus 1. You get y, or you get minus x plus 5 is equal to y. Interesting about this one is the reciprocal of this line is its own reciprocal. And that's because the slope is negative 1 and because the point it goes through is negative. It's kind of a weird and stupid one that they gave us, and I'm sad that they gave it to us. What about this one? This one here is clearly a parabola, and that's not 16 there. That's supposed to be a 6. Unless they added it in later, but I don't think they did. Yeah, that was just me. So, how would we figure out this parabola? Well, you have 2 ways. You could factor it. Let's factor it. I'm going to take an x, and I'm left with x minus 6. That means this parabola has 2 x-intercepts at 0, 0, and at 6, 0. And I also know that the point between that will be its vertex. So what's between those 2 x-intercepts? The point y is equal to 3. X is equal to 3. When x is 3 here, I get minus 3 times 3 minus 9. So that means I know that when x is 3, it's going to be minus 9y. And this is an upward-facing parabola, and that's its vertex, so I should label it. And that's its x-intercept, and that's its x-intercept. So now I can just do quickly like this. And I'm going to label my dots. There. Those are the x-intercepts, rather. And then way down here, 3 minus mine is my vertex. And I'm going to do this. I'm going to make my line green. Like that. And I'm just going to try to make sure it goes through my points. Now, what's lovely about reciprocal is I'm going to draw my reciprocal in blue. Instead of graphing it, I'm going to just flip these dots and figure out where they are. So 0, 0, they're going to share this spot. Instead of 6, 0, it's going to be 0, 6 up here. And instead of 3, 9, it's going to be minus 9, 3, which is over here. So in this case, we're looking at a thing like this. And I'm going to make it a little bit wider to fit my dots. Not bad. It's a little bit off, but not bad. There we go, and that's going to be the reciprocal. Now you just have to flip the dots on the coordinates to. It's always good to label it for full marks. This one stays the same, but this one up here becomes 0, or 0, 6. So I'm going to do that, and it would be right on the y-axis like that. Notice the blue one is not a function. Now, algebraically, how am I going to figure this out? Well, algebraically, you'd have to technically complete the square to figure it out. It's the only way to accurately do it. If I'm going to complete the square, I'm going to say, okay, well, it's x minus 3 is the completion of the square. And when I complete the square like that, I create a plus 9, so I have to subtract 9. And I'm going to say, boom, look at that. Now, actually, you know what? I could have just immediately used my knowledge of the vertex and put it into this formula because I already knew the vertex of the green. Now, if I'm going to find the inverse of that, which is the blue line, I've got to swap the x and the y's. And I've got to isolate the y. Well, it's reverse bed mass. So reverse bed mass says I got to get rid of that 9 first by adding 9 to both sides. Now I can take a square root. So I can take, and I'm just going to get rid of some of this graph here. Actually, there we go. Just make a few copies. So I'm going to take a square root. However, when you take a square root of both sides, you must add the symbol plus or minus. When I take a square root of this side, it just gets rid of the square. And then finally, I have to add 3 to both sides. So I'm going to take this plus minus square root and put it down. And when I added 3 to both sides, I get y is equal to the plus minus square root of x plus 9 plus 3 is equal to y. And I can put it on the other side if I want. But I also want you to notice the vertex of this. This is a square root function, but it's got a plus and a minus, which creates a top and a bottom. And what's the vertex from this equation? You can clearly see the vertex is minus 9, 3, which is what we found out over here already. Now, I could actually have also taken this vertex and put it in instantly into this, so long as I remember to put plus and minus. Now, what happens if you don't put the plus or minus? Okay, I'll show you. Here's the thing we were just talking about. It is x minus 3 plus 9 squared, right? It was also known as this. Oh, minus 9. There we go. Notice the points. It was also written as this. Same graph. Right? And it was also written as this. Same graph. All the same graph. Now, the fast way for you to do a reciprocal on Desmos is just switch the x and the y's. And it'll do it for you. Look at that. No matter which one I switch the x and the y's for. So make that y, make that y, make that x. Does it for you. Just brilliant. That's the fast way. So now it's drawn all the reciprocals, right? But if you want to do it the way we just did it, and you rewrite the formula, you got to do square root x, what was it, x plus 9, and then minus, and then plus 3, right? So there's the top half. How come it didn't draw the bottom half? That's why we had to add the negative number as well. So that's why we had to add the negative number, the plus minus. Desmos does not do plus minus very well. There is a way to do it, but there we go. So this red line represents the reciprocal. Written properly, this one would be the plus part of it, and this would be the minus of it. But there's the reciprocal. But you can see doing the reciprocal by just swapping, not reciprocal, the inverse, just by swapping x and y is really fast. Okay, I got to pause this. I go on and on and on, I know. And I just need to do something else and get back to this. Okay, just going on very quickly to number 4. Now, number 4 is a stupid one, but it says sketch the graph and then sketch one over that graph and then find the equation for both. I suggest instead focus on finding the equation for the first one. So if we look and we find our first differences, this thing is going down by 2. Negative 2, negative 2. First differences are all the same, negative 2. When the first differences are the same, and you've got to make sure your x's are all going up or down by the same amount. They are. These are all going up by 1. When your first differences are all the same, that's a line. And because it's going down by 2, we're looking at a negative line. So let's take any 2 points. So I can see the point 0, 8. And by the way, that negative 2 should be the slope. 0, 8, and I can also see the point 4, 0. Looking at 8 minus 0 over 0 minus 4. So I get minus 0 minus 4, I get 8 divided by minus 4, I get minus 2. So that's the slope. Sure enough, the first differences was the same as the slope. Minus 2x, and what's the intercept? Plus 8. We can find the intercept right over there when x is 0 is 8. So we're talking about that line. That's the line. We're talking about this graph. That's what f of x is. F of x right here is this thing right here. So what is 1 over f of x, which is what they want to find here? Well, that's let's call it g of x is 1 over this line, or this function. How can we find out what the denominator is 0? First of all, let's find out what the correct factoring of that bottom one is. The correct factoring when I take minus 2 out, and I get x minus 4. So that means we're really dealing with a compressed and translated to the right by 4 reciprocal. And what are the restrictions at the bottom? X cannot be 4. X cannot be 4. That's a lot easier to figure out than just setting minus 2x plus 8 to equal to 0. So that means there's only one asymptote. If this is the Cartesian graph, the x cannot be 4 is over here. And it's going to have a horizontal compression, so it's going to be stretched out a bit, but that doesn't matter. It's essentially going to look like that. We could find a couple points on it by plotting these missing ones. Easy enough. But I can already tell you that's what's going to be the graph. And what about this one? What's the graph here? As we already did in the green, graph is like this for this one, for that line. It goes down like this. Okay. And by the way, its x-intercept happens to be the same as the vertical asymptote, and that's because when x was 4 here, y was 0, but y ended up on the bottom, so it became an asymptote. Now, what were the actual values over here? Well, what's 1 over, if this is f of x, which is just essentially y values for this x value, sorry, what is 1 over it? Well, you can just take the same values up above for f of x and put 1 over 16, 1 over 14, 1 over 12, 1 over 10, 1 over 8. So you can just do the reciprocal. So over here, 1 over 2, 0. That's the no, n. But here we get, what's the reciprocal of 1 over negative 2? It's negative 1 over 2, negative 1 over 4, negative 1 over 6. So it starts going small again. And that's because when it was over here, it's positive, but once we crossed the asymptote, we went negative. So all these values are what's being described here. Notice that when we're close to the asymptote, we're going to be approaching y negative. When we're close to the asymptote on the right side, we're going to approach y is positive infinity, and when we approach the asymptote on the left side of 4, we're going to approach negative infinity for y. But let's just see. Let's just put this into Desmos. Or better yet, let's put this into Desmos. And let's let Desmos do the whole thing. F of x is equal to minus 2x plus 8. There it is. Let's make a g of x equal to 1 over f of x. There it is. Let's put the asymptote where I think it is. Y is equal to 4. Let's put the horizontal asymptote in there. Y is equal to 0. And let's plot some points here. Let's make a copy of that. And right here, we're going to create a table. And we're going to just do, some values of g of x. Minus 2 or minus 4, minus 3, minus 2, minus 1, 0, 1, 2, 3, 4. And now for that, let's see, could it handle it? 1 over f of x. I think we had to have some values for f of x to handle. Oh, I've defined g. Yeah, I've done it twice, so it doesn't let me do that one there. That's what's going on. And we can see it's done some points for me. All right. Let's take, and 4, it's undefined. So let's take some values that are really close to 4. Look at that. It's approaching positive infinity. Oh, I got the positive side wrong. And that's my bad. I forgot the basic drawing of the 1 over x, which is stupid of me. And the reason it flipped. The reason it flipped is because I forgot that this is a negative number. And when I rewrote it, I forgot that this is going to cause a flip in the y-axis. So it's not going to be here and here. It's going to flip to that side. It's going to be here and here. So that's what I forgot. I forgot to account for the negative reflection in the y-axis. So that's what we have here. And we can see when I get on the other side of the asymptote here, when I get to 4.001, I'm going to hit negative infinity y values. You see? And 5 and 6 and 7 and 8. And there you go. So we can see the reciprocal of a line becomes a reciprocal graph. And the reciprocal of a line becomes a reciprocal. Of course it does. So that means the reciprocal of a reciprocal would become a line graph when it has 1 asymptote, a parabola when it has 2, a cubic when it has 3 asymptotes, etc., etc. We'll get more into that. Not always, though. Only when there's a 1 as the numerator. So there's that. Now, what about number 5? State the equation of the reciprocal of each function and determine the equations of the reciprocal of the vertical asymptotes of the reciprocal. So this is a line, so the reciprocal is going to be a basic single asymptote reciprocal. This one too, but the asymptote is going to be x is equal to minus 5. This one too, but the asymptote is going to be x is equal to 4. This one too, but the just one asymptote, and it's going to be minus 5 over 2. This asymptote is going to be minus 6 divided by minus 3, so it's going to be 2. X is equal to 2. That's going to be interesting. That's going to have a weird one where they both shoot up. That is going to have 2 asymptotes, and it's going to be x plus 2, x minus 5. So it's going to be, the asymptote is going to be x is equal to minus 2 and x is equal to 5. And this will take a bit more work. But these two will have 2 asymptotes because the reciprocal of 2 parabolas will create 2 asymptotes. This will also, let's see, when x is 3. No, it's just going to create a kind of shoot up on either side. It should be 1 asymptote. Minus 3 and 3, I think. Just 3. So it's just when x is equal to 3. So that's going to be 1 asymptote. That's going to be 2. That's going to be 2. And all the lines are going to just be 1 asymptote. I can get into it in a bit, but I'm just going to pause and come back, I think. Okay, so to continue, we were doing number 5, but I only went through it briefly. So the reciprocal of each function is simply putting 1 over each function. So it'll be 1 over like this. Make that black. And then simply putting the function over and over again. So here are these functions. So that one. And we're going to make a whole bunch of copies. This one we're going to factor. And this one we're going to factor. It's minus 12 and adds up to minus 4, so that's plus minus 6. So we do this, x minus 6 divided by 3, and x plus 2 divided by 6. This simplifies to a third. Then the 3 slips and slides over to here. And this simplifies to 2. Make sure 3x squared plus 1x minus 6x. Nope. This one has to be a 2, I think. Yeah, like that. So there we go. Yeah, I think it was a 4. It was supposed to be a 4 divided by 6. So that becomes a 2 divided by 3, and then the 3 slides in front. My bad. So 3x squared plus 2x minus 6x makes minus 4x, and then minus 4. There we go. Just close this. And then they want us to determine the vertical asymptote and verify your results graphing. So the vertical asymptote here is going to be x is equal to 0, because that's what creates a 0 in the denominator. Here the vertical asymptote is going to be x is equal to minus 5. Here the vertical asymptote is going to be x is equal to 4, because that's what creates a 0 in the denominator. Here you set the whole thing equal to 0, and then you solve it. So that means that's going to be the vertical asymptote. Same with this one. Notice that this one correctly factored gives us the correct translation, and it even gives us the vertical asymptote. There's the vertical asymptote. So you should actually always factor your thing here. This one you just figure out what would be in that bracket to create a 0, and it would be 3. This one's going to look unusual, by the way, because there's no way to create a negative number out of this. This is always going to be squaring to positive. The only resistance is 3. So you're going to see a weird graph like this. And so the asymptote is going to be here. And you're going to see it go up and up on either side of it. It's going to hug the x-axis out here, and it's going to hug the asymptote up there. That's how all these squared ones look like. And let's see. And if you were to add 1 to it, or anything really, you would see this weird bump like that. So let's see if that's true in a second. The asymptotes here are just whatever each bracket would make. So there's 2 asymptotes here, and 2 asymptotes here. Simply set this to equal 0, and you get this. And that's the asymptote. All right, and then if they want me to graph it, I'll graph this one to show you. We'll get rid of all our graphs. Y is equal to 1 over x minus 3, and we'll put in the asymptote. But I'll let you do the other graphs. And notice that if I add, oh, sorry, that was a square. I was trying to show you. There we go. Notice that if I add anything, it creates a little bump instead. And that bump will get smaller and smaller the more I add to it. But if I add a tiny amount to it, let's try 5. Let's try 5. Okay, let's try 2. Let's try 1. That bump gets smaller. Larger, rather. And that's because it's almost creating the same thing as the asymptote. But it doesn't, so it'll be like that. And that's a unique one when you have them squared like that. Not sure what you have when you have it cubed. Okay, it bounces back, and then it does that. So every odd one, it bounces back, which makes sense because you can create a negative number with a cube. All right. And the other ones I'll let you do, but I'll just show you like the double one. Right? And it'll be x is equal to minus 5. So you can see, and actually I should always make these graphs black. There you go. And if you zoom in, you'll see it never touches the asymptote. That's what an asymptote is. It's trying to get to it, but will never reach it. Because it's impossible to have a 0 in the denominator. That's what makes these reciprocal graphs different, and that's what they're trying to teach you. And then we get to 6, sketch the graph, the reciprocal of each graph. So kind of a waste of time, but we'll do it. First we have to, well, they give us fortunately, oh, okay. Actually, yeah, you could just do 1 over looking at that. So they want us, and we could do it one of 2 ways. We could look at the coordinates. So let's start with this one. And we could just put 1 over the coordinates. So if we look at this, this is obviously a line, and we could just grab a couple points. So a couple points on here are minus 5, comma 4. Minus 2, comma 1. I see it goes through at 0, comma minus 1. Actually, here we'll do also the x-intercept, because that's going to be important for the asymptote. That's where the asymptote's going to be. And it has 2, comma minus 3. So if I take my y value and I take my x value and put it over 1, that's what I'm going to get. So that means my y, negative 1 over 2. Essentially just taking my x value and I'm changing all my y values. Okay, and this one is going to be negative 1, which is negative 1 over 1, 1 over negative 1. And this one's going to be interesting. This is going to be, so x is equal to 0 is going to be the asymptote. And then it's going to be, looks like it's 1 over 2, so we start to get positive on that side. So that's going to be that. And essentially what we're going to have is, when we draw the graph, we're going to have something on the, everything to the left of the asymptote is going to be negative. And it's going to do this. We'll do it in purple. And not quite. Try to. That was a bad one. It's not going to curve back like that. It's going to do more like this. Okay, and then over here it's going to do something like this. And to prove that, we just need to know what this line formula is. Well, clearly, the y-intercept is, in the original one, is right there. The slope appears to be negative 1. So we got y is equal to negative x and minus 1. If I put that over a reciprocal, and I take the minus 1 out of it here, like that, and I put a 1 up top, essentially that minus transfers up to the top. You could leave the minus 1 up there to understand what's going on, but it's very much the same thing. And this is what we're talking about now. That negative should have created, actually, let's see, when x is minus 3, actually, yeah. So I got the reciprocal wrong. The reciprocal is actually going to be where that is. So I believe it's going to be x is equal to negative 1. So the reciprocal is actually going to be over here. And I believe I actually got the flips wrong. It's going to be up here and down there. So you can't use that method. My bad. You could take the x values. No, you can't. You'd have to come up with the line formula. So you can't just swap the values. My mistake. So looking at the formula, this is the line formula. And then you'd have to put that over like this, which is the same as this. Well, let's just leave it like this. So I factored out -1, which is actually the same as this. And we'll prove this by making the f of x here the same as the line formula. Use your graphic tools when you're practicing. So there's the line we were talking about, and I can just make my g of x equal to 1 over f of x to prove it. And there we go, and let's put my, there, that's the correct one. Yeah, so I should have realized the x-intercept is the point. I think I did before, and I just kind of screwed it up. And then to prove it, I'm going to put it in formula form. -1 over x plus 1. And we should get the same, the red and the green graph should be the same. And they are. So that just proves that this is 1 over the graph given, and this proves that I correctly did the formula. And I got, as we can see, I got the things incorrect because I did a bad coordinate thing. I think I had to take the y values actually and put the y values over 1. So yeah, that should have been 1 over 5 here. And that should have been 1 over 1 here. So I'll find it -2, 1 on my graph. Yeah. So I had to put the y values over, not the x values. So kind of dumb of me. And that's why here, when the y value is 0, 1 over 0 is the asymptote. Okay, let's go back to another graph. That's that one. So this is an absolute value graph. We just need to figure out the vertex to figure out what the formula is. Looks like the vertex is at 0, -2, which means there's no x translation, which means we're talking about absolute value of x -2. Now we just need to see if there's any stretches. It looks like there's a stretch, either horizontal stretch or vertical compression. Because it's not going up by 1 by 1, it looks like that's 3. So there's another point here, 3, 0. You can essentially find the slope between those two. It's -2, or 0 minus -2, which is 2. And it's 0 minus -3, it's -3. So it looks like it's, oh yeah, 3, 0. 3, it looks like it's -2 over 3, which could make sense. We'll have a look at, we could just figure out, yeah, what you could do is just take some of the x, y values and do it like that. So we can see there's -6, 2, and we can see that there's looks like -3, 0. There's 0, -2. And then there's going to be the asymptote is wherever the y is 0. So this is going to be the asymptote. And there's going to be another asymptote on the other side, because I can see over here that it goes to 3, 0. So that's going to be another asymptote. So we're going to have two asymptotes at x is equal to 3 plus and minus 3. And then it goes 4, 5, 6, 2. So that means over here, if I take 1 over the y, it's going to be -6 over 1 over 2. Then over here, it's going to be at 0 over -1 over 2. So it's positive y values to the left of the asymptote, negative y values to the right. And then over here, that's going to be an asymptote. And then over here, I'm going to have 6, 1 over 2 again. So my guess is you're going to have something like this. And we're going to have an asymptote here and here. And it would appear that it's probably going to, and actually, there's probably going to be a horizontal asymptote down at -2. And there's probably going to be something like this. Let's see if I can figure out the formula of this. So I have some points. I know that's true. I just got to figure out what the stretch is. So I can put an A in front. And I can just plug in some values that they've given me. So I can see -6 is equal to A. Or sorry, 2 is equal to A when x is -6. So we'll make the brackets absolute. And then -1. And we can tell that that's going to be +6. Going to become +6 after absolute. So we're going to get 6a -1. 6a is equal to 3. So a is equal to 1/3. So I believe we're talking about this. Y is equal to 1/3 over x. Oh, it's -2. God damn it. So 4. It's going to be 4 because we figured out this -2. So that means that's going to be 6 over 4. So it's going to be 3 over 2. So we're talking about 3 over 2 as the thing. Let's see if that's true. I don't know if it's going to be 3 over 2 because it should be a compression. Oh no, sorry. 2 over 3. There we go. And then absolute x and then -2. So let's just turn these off so as not to be confusing. So let's see if we got the right one. -3, 0. Is that right? Yep. Yep. 6, 2. Yep. So this is the correct transformation. And now we're going to put x is equal to -3 and x is equal to 3 to see if our prediction is right. And we're going to turn on the absolute value. And there we go. We got the absolute value correct. It does this weird little bend here, which probably will be interesting. Would be interesting to study. And there you go. So there's this weird pointy hat at the vertex. Where it crosses the x-intercepts creates the asymptotes. And it just flips back and forth, positive, negative, positive, between the asymptotes. So we did pretty good on that. And you should actually practice deriving. You can derive any formula given enough points, including cubics and any polynomial if you're given enough points. So that's that one. I think I'm going to stop after this and do a part B. This is a circle, and it's only a half circle. So if you look at a circle, and you'd say this is equal to, find the radius of that circle. It looks like 6. So normally it'd be x squared plus y squared is equal to 6, would create the full circle. Now we're going to isolate the y. Y squared is equal to 6 minus x squared. And then we take the square root. Now when we take the square root, there we go. So it's actually this. And when we take the square root, we're supposed to create a plus and minus. The plus and minus would create the full circle. Clearly this is just plus y's. So the actual formula for this is that, because it's just the top half of the circle. The reciprocal of this, if I look at this, this is where it crosses 0. So we're going to have this weird asymptote here, and this weird asymptote here. And these are all positive. So it's going to be 1 over and 1 over. So it's going to hug like that. It's going to come to here. And then it's going to do it's probably going to do a weird pointy hat thing. And then come back up like that. And actually, no, it might. Let's see. Over here, let's say this. It's going to be minus 5 and 1 over 3. And over here, it's going to be minus 1 and 1 over 6. 103 is higher than 6. So I think it's going to do like that. Then it's going to do a weird bounce. Let's see if that's true. So there's our half circle that happens to have, oh yes, I had to square its radius squared, so my bad. So there we go. And then when I put the reciprocal in, yeah, we get that weird, almost squarish bend. It doesn't do a pointy hat there, but that's okay. It does do this weird squarish bend here. And that would be the same as this. To figure out the roots, you would set this to equal to 0. First you square. First you square off. First you square both sides. So you square the right side to stay 0. Then you add x squared to both sides. Then you square root. When you square root, you get x is equal to 6, and x is equal to minus 6. And that's your asymptotes. That's how you figure out your asymptotes. Okay, that's that one. So you could either do it from the plot points or from the graph, or figuring out the equation. If you're doing it from the plot points, you would say, okay, well, this is minus 6 comma 0. When I take the reciprocal of 1 over 0, that's my asymptote. Then you can say, okay, well, that's about 5 comma 3, but not quite. So that's going to be minus 5, rather, comma 1 over 3. And then when you get enclosed, you can say, okay, well, that's minus 1, almost 6. So it's going to be 1 over 6. And you can say, well, 1 over 3 is bigger than 1 over 6, which means it's going to come down and hug. And you know that it goes through because there's no asymptote there. And then you know it's also going to mirror because the right side of this graph is the same as the left side. It's symmetrical through the y-axis, so the reciprocal should be symmetrical through the y-axis. Same with this. So if that's the asymptote, we're going to have like something like that. It's going to be the same thing on either side of the asymptote. Okay, so looking at the last one. If you just plot some points, you can see that it goes, okay, roughly minus 4 comma 6, minus 3 comma 4, minus 2 comma 2, and minus 1 comma 0, and then it goes 0 comma 2, 1 comma 4, 2 comma 6. And if you find the reciprocal of that, the reciprocals become minus 4 comma 1 over 6, minus 3 comma 1 over 4. Those numbers are getting bigger. Minus 2 comma 1 over 2. And then minus 1, x is equal to minus 1 is the asymptote, because you can't do 1 over 0. Then it comes 0, 1 over 2, 1 comma 1 over 4, 2 comma 1 over 6. And you can even say infinity will be 1 over, will be almost 0 or approaching 0, because we can see that's what it's doing. And we can also say, okay, well, negative infinity will do the same. Y will approach 0. And as we get close to x is equal to minus 1 on this side, we approach infinity y, positive infinity y, because all the y's are positive. And the same here as we approach x equal to minus 1 on this side, y approaches. This is what this means. plus infinity. And I can tell that because these y values are getting bigger and bigger and bigger. So as I get closer to 0, where the y values here get smaller, 1 over a small number will result in a bigger number. Whenever you decrease the denominator of a fraction, the result gets bigger. Okay, so that tells me that my graph should look something like this. And this is going to be x is equal to minus 1. And that's because the reciprocal, which is roughly, I think it's going to be like x plus 1. It's probably stretched or something. Probably 2. It's because the reciprocal here to make 0 is x is equal to minus 1. And it acts like a square. By making everything positive, it's kind of like squaring it, because squaring makes everything positive. There's no way you can have a negative result from this formula. So let's have a look. Oh, and how would I figure out the actual formula? Okay, so we have the actual numbers here. We know the general formula of this is y is equal to a, some sort of stretch, over the absolute value of x plus or minus, possibly. We can see this has been translated to the left by 1, so we can say absolute value like that. And we can see it has not been raised up or down, so there's nothing there. Now we just need to figure out a, and we figure out a by putting in some values of y. So let's use the first one. 6 is equal to a, absolute value, and in this case, x was minus 4 plus 1. So inside the brackets, you get minus 3. When we absolute value that, that becomes 3. 3a, which means a is equal to 2. So that means up here the formula is this. When I take the reciprocal of that, it's not reciprocal, no, that's derivative. Forget what reciprocal is. Reciprocal of y, this, we get 1 over that. Okay, let's see if that's true. Here's the f of x. There's our graph, and there's our points that we found. 1, 4, minus 3, 4, minus 4, 6. They're all there. Here's the reciprocal. And it's when x is equal to minus 1. So sure enough, we got that right. But here's also the formula for the reciprocal. It'll be the same as the blue graph. And you can see when this is minus 1, this would become 0. That would make the whole denominator 0, so you can't have that. Now it's possible to have negative numbers. You just have to lower this down. And then the reciprocal would look like that. And that's because we pass through the x intercept twice and create 2 asymptotes. But that's only if you lower an absolute value. If you raise an absolute value, you won't have an asymptote. You'll have this weird bump. That's because there are no way to create a null value in the denominator because we raised it by 1. Just study more and more and more and study your graphs more and more. Now I have to stop, so I'll do a part 2 later.